Hello and welcome. My name is Malte Mundt. I'm working as a field application engineer for BlackBerry QNX, and we will talk about kernel event tracing and system profiling. First, I'd like to give you a quick overview on what kernel event tracing actually means. Then we'll discuss the basics on how to use the system profiling tool to visualize data from a kernel event trace. And then we will dive into the details. We will be looking at three main areas. The first one, processing time. So how long, how many milliseconds or even microseconds did your code actually execute? Then dependencies. Often you will be using OS services or ask another process to do work for you. We will uncover this so you can find out what system components you depend on and which ones may slow you down. And finally, bottlenecks, issues where something is slow, but the CPU is not fully loaded. Let's get started by defining what we are actually talking about. So to understand what kernel tracing is, I first want to clarify what I mean when I say kernel. The context here is QNX, and most of you know QNX is a Unix-like OS, so it is similar to Linux. But when looking at the kernel architecture, you see QNX and Linux are fundamentally different. When you look on the right side, you see that in Linux, lots of OS functionality is part of the kernel itself. When you look at the left side, you see that in the QNX OS, basically everything is a process. That includes a lot of OS functionality. Why is this? First reason is to support freedom from interference. No component can override the kernel or something else. And the second reason for having a microkernel is risk reduction. The microkernel only does scheduling, memory management, interprocess communication, and such things. Many complex operations like hardware drivers and networking stack and so on are run as separate processes with reduced privileges outside of the kernel. Yeah, that makes it very hard to compromise the kernel. So everything is a process, and they are coordinated by the microkernel. And for the microkernel, all processes are equal, which means all can use the same API. You have full POSIX wherever you are. What kernel event tracing then means is logging things that the kernel does in the system. The kernel is always seeing everything, all processes, all threads. And because QNX is a microkernel, this includes OS services as well as applications. Everything running together, being scheduled, interacting with each other, and so on. This gives you a completely different view on your system. It's totally different from a normal debugger where you usually look at just one process. When we are talking about kernel event tracing, we basically are talking about logging everything the kernel knows about. So we have to understand what exactly does the kernel know about. First, it of course knows about the creation of processes and threads. Then it schedules these threads, and the threads do all kinds of things. For example, when a thread does something that triggers a scheduling decision, then the thread changes state. And this is done by the kernel, and this is something that it can log. Then when a thread communicates with another one in a different process, this is also handled by the kernel. When you use the QNX microkernel as a hypervisor, which is also possible, you will create virtual machines, which are, in the end, special processes. And you can see what they do, especially when a VM is doing something outside of its guest OS, for example, interacting with a shared resource that is managed by some other process in the system. The kernel will know about this, and yeah, so can you. With all these events, we can observe what all the threads in our system are doing. This can be very useful. For example, if you have a process that links against some large framework, you may find out that it makes a lot of kernel calls, or you can watch which application is accessing which hardware resources. So when something in your system is too slow, you can find out if it's really your own code that is too slow, or if it's someone else's code that is slowing you down. And this becomes even more important nowadays when more and more third-party code is incorporated into a system. Okay, let's now take a look at visualizing the data from a kernel event trace. When you first open a kernel event trace, in the system profiler, you see a summary. In the kernel event trace, there are lots of events, and each event has a microsecond accurate timestamp. So the system profiler can quickly calculate the actual overall CPU usage during the time of the log. It gives you a first indication. For example, if you are expecting a fully loaded system, A lot of blue here in the pie chart will come as a surprise for you, as it means idle CPU time. Kernel activity, yellow, is interesting because we just learned that the QNX microkernel doesn't contain a lot of OS services. Those are all included in user space processes. So if kernel here is extremely high, something is going on. Then interrupts can also be interesting. The red color is just interrupt handlers. So not threads scheduled because of an interrupt. Next, the CPU activity view. This shows you exactly how active our CPU cores actually were. This is great for logging during certain use case scenarios, for instance, booting or some advanced feature. You might think your CPU cores are fully loaded, but they are not. Or they are, but not with what you expected. And this is where the next view comes in here. It's the CPU usage view here on the right. It shows you exactly who or which process is contributing how much to the total CPU load. For example, if you spot one process causing constant base load, I would recommend to optimize this. Everyone else will benefit and get faster. And for peak load, you see which processes contribute how much, so you can target the ones with the largest share. Now, what we are seeing here is the main view we will be working with today, the timeline view. The system profiler sorts all the events in the log by owner. And owner is the source of the event, process or thread. For each owner, you will see a timeline, a horizontal line. And each little vertical line is one event. Next to every process name, you will see a little plus sign. You can click on this and open it up, and you will see all threads of that process with their events. The key feature here is the zooming. So usually you will go to an area with lots of events, mark it, and zoom in. In large systems, which we are having more and more nowadays, we have many, many processes, even more threads. Additional filtering is very useful. For example, filtering to only see the most CPU-hungry processes. Okay, with that being said, we can now discuss the basics of working with the timeline to analyze processing time. So when you as a developer get told something like function X in your application is too slow, you can try to make it faster. But first, it's important to find out how much time it actually needs, right? So when looking at processing time, what we do is looking at threads being scheduled and for how long. In the timeline, the state of each thread is shown with different colors. And that's what you see here. So when a thread is ready to run, but not running yet, it will be drawn in a thick line in dark green. And then when the thread is scheduled, it is in the state running, which is then actively consuming CPU. And in the timeline, this is drawn in light green. Light green for the first CPU, and for other CPUs, other light colors, let's say. And then when the thread is not running, it is blocked, which means it is waiting for something. For example, because it is waiting for an event or for a message. And there are different states, and those are shown also in different colors. Let's go for an example. Let's assume you have some kind of event happening, and in that event, when that happens, you have to quickly calculate something. I have simulated this. I have written a little program that is searching for the first 1,000 prime numbers. I start it, and I do a kernel log, and in the timeline, I can see exactly how long this takes. 9.5 milliseconds. Great. Okay. But when there is more going on in the system, there are times when suddenly my calculation takes longer than normal. And yes, it depends on what else is going on in the system. If you have not configured scheduling priorities, your thread is scheduled round robin with others. We have here one other process with a thread being very busy, the CPU burner, right? And this means suddenly our calculation takes longer. It takes suddenly now 17.9 milliseconds. Yeah, when we look at the different timelines of those processes, we clearly see what's going on here, right? The round-robin scheduler is using time slicing. So each thread can have its fair share of CPU time. Your thread gets stopped from time to time, waiting in ready mode, while the CPU burner thread is active. Okay, and then let's say your system is very busy. And next to your thread now, we have 2 other threads that are being scheduled on the same core. What happens now is that a ready queue is building up. All threads wanting to run are queued up. The longer the ready queue becomes, the longer it takes until your thread gets allowed some time to run. So your code seems to get slower and slower the more things are going on in the system. Now, we have the QNX OS, and that's being real-time capable, right? So we have a mechanism to increase determinism, and that is the use of scheduling priorities. The QNX scheduler will always first look at the priority. So let's increase the priority of our calculation thread. Take a look at the diagram on the bottom left here. We can see what the scheduler is doing. While round robin just means taking turns on one priority level, a higher priority will preempt immediately. We do this for our little thread, and suddenly it's back to its original speed, 9.5 milliseconds. We have the same total CPU load as before, but a completely different behavior. In this configuration, these 2 CPU burners can no longer interfere. Now, there are only 2 things that could slow our calculation down. First, a thread at an even higher priority, okay? And of course, second, another thread on the same priority. With multiple cores, the scheduler distributes all ready threads onto all available cores, but usually you have more threads than cores. So priorities can get very important for your performance. Another thing that can impact performance are interrupts. You can look at the time it takes from the reception of the interrupt until the interrupt handler gets called. Then from there, that's usually a driver that attaches an interrupt handler, which gets called when the kernel sees that the interrupt happens. That enables you to see exactly how long the interrupt handler took to be executed. This should normally be a very short period of time. When an interrupt handler is done, in the end, it can ask the kernel to wake up a thread to do further processing. And you can also see how long that took. And this interrupt thread is executing then in the full POSIX environment. It will run at the priority you assign to it. Okay, next topic, dependencies, the interaction between components. When we are done with searching prime numbers, if we look at the timelines here, we can see that after it is finished, some other process suddenly gets executed. defc con hit, it is a text console. That is because our example prints out its result to the text console when it's done. Why can this become important? Because it's an example of client-server relationship. And with the system profiler, we can visualize this. Anytime a program needs something from another one, it becomes a client of a server. Servers usually are drivers or OS components, such as a network stack. The client sends a message to the server with some kind of request. There could be data to be sent, could also be asking for data. The server then gets active and replies to the client. The whole thing is called IPC, inter-process communication. People often are not aware that they are initiating an IPC activity. This can happen implicitly, for example, in libraries or frameworks. So when you see a certain process being extremely busy, it may be a server that is serving many clients. The CPU load of a server that's indirectly caused by their clients. And we can use a system profiler to examine this. When you find out that you depend on a server, so you are the client, you can have the system profiler calculate how much time you have to spend waiting for it. You can examine what it's doing. And of course, you can look around, like we discussed previously, if there are other processes taking away CPU time from the server you are waiting for. Okay, next, yes, we can look at a typical scenario for a client-server relationship. I have used here as an example a program called TTCP, short for test TCP. It's a very simple program which is sending out data over the network. while running this, I'm doing a kernel log, open the log. First thing that you can do in this case is to apply another type of filter, the IPC activity filter. So now we see that our test TCP app is a client to various servers. It's very obvious. It's talking to the network stack. So let's zoom in on this. Now we see something interesting. Our application isn't doing a lot. Most of the time, the networking stack is active. The network stack is the server here, and our test application is the client. It obviously spends most of its time waiting. So let's look at something called the client-server CPU statistics. For our little TTCP, we can see here that while itself it didn't do a lot, it is responsible for a much larger amount of CPU time. The time where we as a client put a burden onto someone else is called imposed time. So it might be worthwhile for you to look at the imposed time for all your processes to find those that are really hungry. Now, let's talk a bit about the frequency of IPC. If you send data to a server, it can matter if you send it in small chunks or in large chunks. Why? So every time you send data, you as the client need to prepare a buffer for it, right? And then on the server side, the server has to be prepared for all kinds of requests. So the time the server needs to process a request is usually a combination. There's often a fixed amount of time needed to process a request, regardless how much data is coming in. For example, the network stack may have to prepare an Ethernet packet, and then there is additional time, sometimes much and sometimes not so much, depending on the amount of the data. And finally, if the server is a driver for some hardware, it has to interact with that hardware, which will also cost time. Okay, so let's look at the logs I did here. In the first one, the upper one, I run my test program TTCP again, and I'm sending 800K to the network stack for processing. My test app is now the client. The network stack is a server. I can use the general statistics to show the total time my program has waited for the server to reply. It's 16 milliseconds. And then look at this. About 100 messages have been sent. And why is this? This is because I configured the test application to send 100 packets, and each packet was 8K in size. So for 800 kilobytes, 108K packets. Next, I had exactly the same scenario, but with one big difference. I now send 1K packages, 1 kilobyte packages instead of 8 kilobyte packages. This way, instead of 100 messages, TTCP had to send 800 messages to the network stack. 8 times more, okay, for the same amount of data. So it was 8 times more message passing. How long was the total wait time? Of course, not 8 times more, not even twice as much. But still, we see that this 8 times higher frequency of IPC has caused some slowdown. So message passing frequency and size is important. I think if you learn one thing from this today, it should be don't send large amount of data as a ton of 1 byte small messages. If two processes actually share tons of data, why not consider a shared memory object? Basically, it's an area that both could map into their virtual address space and work on. Of course, it's not as cleanly decoupled as with message passing, but it can be faster. Okay, third big topic for today, very interesting, I think, bottlenecks. I guess we all know this scenario. When you, for example, press a button, you press this button, and it takes too long to react. And in that moment, you assume The CPU is at full steam, totally busy. But when you look at this with the kernel trace, you may find times where it is not busy. And that's something with a normal debugger, you will never find this easily because you don't see the wait time. With system profiling, you can. So often behind this is resource contention. It means that multiple threads want to access a certain resource at the same time. Often this resource is guarded using a semaphore or a mutex. If you see such purple bands like here in the screenshot, your threads are waiting for a mutex. In that case, you have to find out why a mutex is used here. What does it try to protect? Often a mutex is used when changes happen in shared data structures, or when hardware registers are involved that can only be accessed by one thread at a time. Could also be some high-level application state changes that must complete before moving on. Whatever it is, to get maximum performance, it is key to reduce mutex wait times. The corresponding code has to be examined if the mutex can be locked later or can be released earlier, or if it really has to be a mutex. For example, if many threads just read a data area and only one writes to it, for the reading, you don't need a mutex. You could use a read-write lock that only stops the thread trying to read when the writer is active. So what the system profiler does here, it shows you the wait time, where you see how long your threads had to wait. It also helps you identify which thread holds a mutex for the longest time while the others are waiting. And we have in this screenshot is also a scenario of a deadlock, where obviously one thread forgets to unlock the mutex. So in the end, everyone is waiting for each other. Now, let's talk about a common bottleneck, which is when servers are being hit with requests by multiple clients. Servers are processes managing a certain resource. And the bigger a system gets, more and more clients are talking to multiple servers, and they all depend on each other. So now a different example to illustrate this problem. I've chosen a setup where QNX is being used as a hypervisor. For those of you who haven't done this, it's like a normal QNX OS, but with the ability to create special processes that can run virtual machines. These are called QVM, short for QNX Virtual Machine. So I have this embedded system. I telnet into it. I telnet into it 2 times. So I have 2 remote consoles open, okay? And then in the first console, I start a Linux VM. I start a VM, and inside is a Linux running as a guest. And I do this at priority 10. And in the second console, I also start a VM, but this VM will run QNX as an OS inside the VM at priority 100. Let's say I do this because it's safety critical. Now, in the Linux console, I have 2 consoles. One is now in Linux, one is for QNX, right? So in the Linux console, I do something that leads out to a lot of characters being printed out to the console. Let's look at what this means from a kernel trace point of view. First, we see the Linux VM talks to the console driver of the hypervisor, devcpty. That's because the console in Linux uses a virtual driver to redirect its output. Next, we see the console driver is now talking to the telnet daemon. That's expected because we are having here a remote console. And from there, we can see the telnet daemon sends the text, the console data that is being printed out of the console, it sends it to the networking stack to be sent out. Now, with all these servers involved, we can observe something interesting. The time the Linux VM is waiting until these operations are complete is always the same. Now, additionally, we let the QNX virtual machine also print out some text to its console. So this is now the QNX OS as a guest on top of the QNX hypervisor. So it also now prints out text to the console. The same interactions apply with defcpty and so on. And what we see is here that thanks to its high priority, it can pump out its text without any delay. The processing time is exactly the same that we previously saw for the Linux VM when it could use all the servers on its own. When the Linux VM invokes any servers, why does their processing time not impact the request sent by the QNX VM? This is because of priority inheritance. Not only has the QNX VM itself a higher priority, also all servers which work on behalf of this high priority client will work on this high priority. So when serving multiple clients, this avoids a bottleneck situation where all clients equally wait for one server. But as you can see here, if you are the low priority client, you might have to wait much longer when a high priority client is keeping the server busy that you need. Okay, let's look at another source of a bottleneck situation. We said we have two VMs printing out text. So the system should be fully busy doing this and the CPU load should be maximum, but it isn't, as we see here. Looking at the timeline again, when we move around a bit, we see more and more of these red lines. And some of them are really long. This red appears when a client wants to send to a server, but the server is currently busy. It's not waiting for messages, but doing something else. This is called the client is send blocked. And we see this not just for one thread, but many of our threads are send blocked. What we can do now is we can turn on priority labels. They show us whenever the priority of a thread changes. And what do we see? We see the defcpty, this console driver thread priority, is changing very often. What is this? Is this priority inheritance? Yes. The console driver is processing a request from our low priority VM, and at that moment, the high priority VM sends a request. Defcpty priority is increased immediately. Okay, this helps minimizing the wait time of the high priority client. We just discussed this. But why the priority of defcpty is changing so often? Well, when we look closer, we see it's actually bombarded with many, many requests. As soon as it is done with one request, the next is already waiting. So basically, it runs the entire time and is never fast enough to process all requests, although we have enough CPU cores available. So what we find out very quickly here is this thing is single-threaded. So it can only use one CPU core, never more, never more. Being single-threaded is not a good idea for high performance. Here, okay, it's just an example. Printing text to the console is in reality not time-critical, but we learn a very important lesson. Servers working for multiple clients should be multi-threaded to maximize parallel processing. Okay, that was the most important stuff. So let's make a conclusion. What have we discussed? How to identify sources of high CPU load, what the ready queue is, and how scheduling priorities can help you. And we discussed how to measure interrupt handling times. Then we talked about dependencies, the client-server relationship, how clients put burden on servers, impose time, and why the frequency of inter-process communication matters. Sending the same amount of data in larger chunks is better. Yeah, and then we discussed bottlenecks, how threads can wait for each other because they share some kind of resource, are blocked waiting for mutex, and so on. We looked at how priority inheritance can help minimizing wait time. And we looked at the situation where everyone was waiting too much just because one process was single-threaded only. In summary, kernel event tracing and system profiling help you to understand how everything in your system is connected. You can inspect individual processes to find out how much CPU they use in which situation. And you can find out how any processes depend on other system components. All this will help you, hopefully decide for the best optimization strategy so you can build the best possible system. That was my mission for today. And if you want more, I recommend you to read the extensive QNX product documentation that goes into more details regarding kernel tracing and system profiling. And by the way, the system profiler is just one of several tools, part of the QNX Momentic tool suite. We offer extensive online trainings on this. Thanks everyone for attending today. It was a pleasure to be your host. For now, I'm going offline. Thanks a lot and have a nice day.